Dear colleagues, we continue with the second lecture of the day. And we would like to thank Professor John Pomeroy that he agreed to give a lecture to us today. So Professor John Pomeroy is Distinguished Professor in the Department of Geography and Planning in University of Saskatchewan, and he is also Director of Global Water Futures Program and Director of University of Saskatchewan Center of Hydrology. Professor Pomeroy, so floor is yours, 45 minutes. And then 15 minutes for questions.
Great. Thank you, Dmitry, and thank you, Dr. Galvan, for inviting me to the School for Young Scientists. I want to speak today about how we might use advances in hydrological sciences to conceptualize and parameterize hydrological process models in data poor or ungauged regions. And I'll go through some examples from Western Canada, but as Canada is a cold region, I think for those students who are based in Russia, there will be many aspects of this lecture which will be familiar to them in terms of the needs for cold regions process physics to be incorporated into their models. And Russian scientists have in fact led the way over the years in developing this type of research. So I will fire up the screen here, and there we go. So hopefully you can see me all right. And so I want to recognize a few of my co-authors who are colleagues and students over the years who have contributed data, which I'll be showing you here, including Tom Brown, who retired just a few months ago after a 50-year record of working as a cold regions hydrological modeler at the University of Saskatchewan. So how might we solve hydrological problems in data poor basins? Well, there are a number of issues and opportunities that we have. One is that streamflow data poor basins usually not very useful. It's incomplete, or it doesn't exist, or it might be on basins that are very, very large, but we want to predict on river basins that are much smaller. And there are a number of reasons that typical regionalization approaches and model calibration approaches are highly restricted. It can be also very uncertain data due to river ice breakup and other situations which make the stage discharge relationship uncertain. Usually, where we don't have a large density of streamflow observations, we also lack meteorological observations. So the weather stations are sparse, and this is typical in cold regions in northern Canada or in the high mountains. And this means that we might need to use weather models, reanalysis data, meteorological models to fill in that data. We often might have a lack of good mapping of land cover characteristics, but satellite imagery continues to improve and currently provides very good surface vegetation cover. The hydrography, the hydrometric network of streams, lakes, ponds, wetlands is quite good. And sometimes you can infer soil information and even initial soil moisture conditions from satellites, which are useful. And of course, some of that can be used for assimilation as well, but I won't address assimilation here. Digital elevation models are becoming excellent around the world with improvements in satellites and airborne LiDAR. This is particularly important in landscapes that are formerly glaciated and tend to have very flat topography. The many regions, particularly agricultural regions, have adequate soil maps and other information. Groundwater information is often missing, which is a problem everywhere, and small-scale water management information can be uncertain or simply missing. Also, remember, in all river basins in the world, we have climate change and land use changes, which are causing a loss of stationarity. So even when we have streamflow data available, its use for future predictions has to be very nuanced. It doesn't make sense to calibrate a model for the 20th century when we're going to apply it for the late 21st century. So the big question is, can we find appropriate data and solve equations for hydrological solutions in data poor regions that are consistent with hydrological science? And I'll dive into a bit of philosophy here and a little bit of artwork, so bear with me, and then we'll get into the guts. Part of this is a fundamental question that hydrology has to answer itself. Is hydrology a science or is it mythology? And so what do I mean by that? Well, we still have many conceptual hydrological models around. It seems that every model ever written still persists. And some of these are, in fact, dating back to the 1960s and 70s with very little change. So these early models in particular are very conceptual, and they need to be calibrated. And that means that one has to accept the errors in these models and live with it. So is accepting those errors the price of solving hydrology? Do we have to have very simple models that we know are physically incorrect in order to predict? Well, there are a class of models that strive to predict whilst incorporating new scientific advances. And these are really the future for hydrology. So my argument is that we need to stop hydromythology now. And here's an example of hydromythologies. I define it as older concepts that have been dismissed by scientific investigations, but persist in hydrological models. One is that evapotranspiration and snowmelt can be estimated by simple indices, bulk transfer functions of temperature and wind speed, temperature index melt of soil, snowmelt. Another is that frozen soils behave the same as unfrozen soils, and that we can simply calibrate an unfrozen soil routine to behave for frozen soil conditions instead of recognizing the contribution of the ice to changes in flow through porous media. Another is that the world is flat and slope and aspect do not matter. It's amazing to see the hydrological land surface schemes applied in mountain regions around the world that consider the Earth to be flat and have no slope and aspect. And of course, that's absurd and degrades mountain forecasts, which are the source of many of our rivers. Another is plants can be represented by conceptual parameters, that we have steady state evapotranspiration, that we assume the fully developed boundary layer without advection or feedback from the canopy, that root zones are fixed. All these are wrong. We know that roots grow deeper in drought and shallower in wet periods. Soil moisture withdrawal curves change with time, depend on more than texture, but we still leave these things in our models. Snow melt is a source of water for over half of humanity. Yet we, in many models, tend to assume that snowfall equals the snowpack available for melt, that the snow is not intercepted or redistributed by wind, it's not sublimated, and we often don't apply wind undercatch corrections to our snowfall gauges. So this can put our estimates of snowpacks available for melt to be seriously in error. Another is that soils can be represented as uniform homogeneous porous media that do not have macropores, that we can apply Richard's equation in Greenamp very easily and heavily calibrate them from Streamflow, and that they don't have slope. And of course, all these are rather absurd. Another is that physically based equations can produce physically based solutions. Well, this is an area where we trick ourselves quite a bit. If we calibrate parameters to unrealistic values that have no basis in reality, we can produce model behavior that's inconsistent with reality as well. And the model no longer becomes physically based. It becomes a mathematical toy. Another one that really bothers us in Canada, creates great problems for us, is that the basin area is assumed to be all able to contribute to streamflow. And many areas are poorly drained and have non-contributing areas, which are quite substantial, that we have to address. And then another is this idea of very simple binary flow pathways for runoff generation. Flow is either quick or slow. And this occurs in older conceptual models and goes back to Hortonian overland flow and a conceptual subsurface flow. But in reality, we have it's a transition between these and with variable solarities depending on storage and other states in the basin. So, so there's lots of other things going on that we often miss in our models, and we often say, well, we'd like to have parsimonious models. So we look at parsimony, and that's Scrooge, by the way, sitting there being very parsimonious with his porridge, and saying that, well, parsimony is extreme unwillingness to spend money or use resources. Another definition is it's a scientific principle. Things are usually connected to behave in the simplest and most economical way. This is an assumption, it is not a conclusion. And process hydrology and process physics and hydrology do not always support parsimony. It doesn't always work like that. And so our models need to reflect that when necessary. Another issue is identified way back by Keith Bevan is Pygmalionism, and equifinality, and I'll add self-deception to that. And this is that we build hydrological models. It's hard work. We spend decades at it. We tend to name them. Sometimes we become great supporters of the models that we create. And then these models age. And then what do? We defend these models and say, yes, this is the best model ever. So what are we defending them against? Well, sometimes we're defending them against scientific advances. And if we do that, we can become an enemy of science and actually argue against the utility of scientific advances in models. So we need to find ways to break that cycle. There's many ways to become deceived as a modeler. One is through equifinality, many sets of parameters leading to similar hydrograph simulations. We can think we can get it right. We can overcalibrate physically based models based on Streamflow, such that they no longer have a physical basis. And as I said, that makes them no better than a highly complex mimic of hydrological response. And so our way forward should be to evaluate our models by the veracity of their internal function and their ability to predict multiple components of the hydrological cycle. Should be a hydrological cycle prediction as our goal, not just Streamflow synthesis. And as I mentioned, there's some old models sitting around, and I call these zombie models, the undead models. They persist without life or incorporation of new ideas, and they're dangerous. As you know, zombies are bad for your brain, and models that don't have a connection between current science and model development would fall in this category. So we want models that bring in the wonderful new discoveries in hydrology and can bring them in easily. So one approach to hydrological modeling is process-based. This can be multi-scale modeling. The idea is that you use modeling, field studies, and remote sensing together to find appropriate model structure and parameters. This can be through integrated observation and prediction systems, as WMO has recently recommended. If we have appropriate parameterizations based on this hydrological understanding, we can diminish those hydromythologies and root them out of our systems. It's a scientific, satisfying, and robust approach for dealing with non-stationarity, which we definitely are for the rest of this century, if not further. And I think it's important to embrace our failures at modeling. When a model fails, doesn't mean we have to calibrate it. Maybe it means we need to look at it, think about the appropriateness of that model structure, the model approach, how we've set it up, and see how we can learn from that to improve the modeling. And with that calibration being an approach for routing, for determining routing parameters and others where necessary, but not the first resort for setting multiple large numbers of parameters for a model. So to address some of these problems, several years ago, we set up a modeling platform at in Environment Canada and the University of Saskatchewan. We call this the Cold Regions Hydrological Modeling Platform, but it includes all the components you would need for non-cold regions modeling as well. We started this in the late 1990s. It's a modular modeling system. It's flexible and uses object-oriented programming. So the platform allows you to assemble a purpose-built hydrological model from dozens of C++ modules that relate to hydrological processes and data processes. It's based on a long series of research in Western Canada and elsewhere. There's a wide range of complexity of options available in here, because sometimes you have very good data and lots of information to parameterize and drive a model, and sometimes you have very incomplete data and very incomplete information to set parameters. So having simpler and more complex versions available within a modeling platform is quite useful. It also allows you to do a model intercomparison and falsification within the same modeling platform. The user builds the structure based on the modeling objectives. Maybe you just want to predict soil moisture. Maybe you want to predict stream flow. Maybe you want to predict evapotranspiration or snowpacks. You can set up models for these specific endpoints and anything in between. There's no facility to optimize within the modeling platform, though people have learned to do it outside, of course. But the objective is that parameters are set by knowledge, and that if the model results are incorrect, do not reflect reality, it means that we don't understand what's going on. So that's the point, and then you go back and try to understand this better. It's a spatial basis is the hydrological response unit. So it's a landscape unit with characteristic responses, horizontal interactions amongst HRU, and the model tracks state variables and flows within HRU and sums to subbasins in the basin. There's a single parameter set per HRU. So each is essentially a control volume in which we apply coupled energy and mass balances to it, and then link these to a broader set. We can also change the model HRU by HRU. So you can have a different model in different parts of the basin with different model structure depending. So it allows you to include agricultural areas, high mountains, forests, and model them somewhat differently. The routing is rather flexible. We include blowing snow, which has an aerodynamic routing controlled by wind flow. We have drainage networks, overland flow, subsurface flow, stream flow for stream flow, and then subsurface flow fields for groundwater. So groundwater can drain in a different direction than surface water if that's the case. It allows for variable contributing area calculation of connected and contributing basin areas, things like fill and spill runoff generation, which are important in some environments, and very flexible structures. So you can figure it very differently for different environments. And then river routing, basic river routing to connect the subbasins. Muskingum is often preferred. So you can see a point where you can download it and read some papers on it at the link below there. All right, so I wanted to jump to Western Canada, to the Bow River Basin, which is upstream of the city of Calgary, Alberta, which has been an area of great interest for us. And I want to show you some applications in there. The Bow River Basin drains from the Canadian Rocky Mountains to Calgary. It is covered by national parks and a UNESCO World Heritage Site. So it's a large protected landscape, but the lower parts of the basin are subject to forestry, forest cutting, agriculture, and recently we've had some severe fires, we've had glacier retreat, and we've had urban growth in Calgary, and also some very severe floods. So the most expensive flooding disaster in Canadian history occurred in June 2013 with floods along the Bow River, which devastated the city of Calgary and other communities along the way. What's fortunate for us is that we have a number of hydrological observatories. These are research basins which date back to the International Hydrological Decade and were founded in the early to mid 1960s, particularly Peyto Glacier and Marmot Creek Research Basin, which go back very early times. We've added others to them over time as well. And we can use this information to better set up and understand our modeling and to evaluate them as well. You see, we have a decent set of hydrometric and met stations in the basin, in the lower part of the basin, but not much up in the high mountains. And most of the flow is coming out of the high mountains down towards the prairies here. So how do we predict stream flow in the basin? Well, we needed to improve our understanding and description of the hydrological processes. So that's been a continuing effort. We wanted to incorporate that process knowledge into hydrological models, run them at fine scales, and then scale them up. And so we have lots of good information available from examining this clear-cut forest site here, or using things such as drones, UAVs with thermal imagery to look at surface temperature variation from clear cuts to natural forests to help us in better implementing an evapotranspiration scheme in the region. I mentioned Marmot Creek Research Basin going back to 1962. It's just a little bit smaller than 10 square kilometers. The higher parts of Marmot Creek are alpine environments. We have forests in the middle parts, a little bit of meadow at the bottom. There are clear cuts, which were put in there experimentally in the 1970s and 80s to look at the effect of forest harvesting on streamflow. And there's a long series of history of sub-basin gauging and net stations throughout the basin, including precip measured at the lower part and the upper part of the basin. It's a snowy place, about 70% snowfall and 50% of precip formed runoff, so it's a high runoff ratio. That's the Winter Olympic ski hill from 1988, the 88 Winter Olympics next to it. So that gives us nice logistical access into a Marmot Basin. Here's some of the upper parts. You can see it's very wind blown, lots of snow redistribution by wind, and tough place to operate weather stations, but we do it. One aspect is blowing snow. Snow blows into the basin from upwind from the west, and of course this is a two-phase flow via saltation processes near the ground of a hopping motion or suspended blowing snow processes more than a few centimeters from the ground. And here you see some photographs of snow blowing into a basin and snow being suspended as it blows along. And this is actually a very important process. We lose in the alpine 20 to 30% of the blowings of the snowfall to sublimation from blowing snow in that environment. And but we also gain in certain subbasins of Marmot Creek vast deep drifts exceeding 4 meters, and in other places scoured down to bare ground. So we have to account for this redistribution of snow in order to get any kind of snowmelt model to work properly in this environment. And this is the kind of redistribution you might get over an alpine ridgetop. Snow scoured over the north and ridgetops and then deposited in deep drifts down on the south faces. And of course, then if it's all deposited on the south face, and that gets greater melt rates due to solar radiation, very different situation than if the snow was blowing from south to north in here and putting the drifts on the north faces, and creates differences in the snow cover depletion curves that control runoff generation. Here's an example of some of these snow surveys on this basin. You can see very deep snow in the forest tree line, and in the bottom of the south face, top of the south face, very little in the north face and the ridge top. And when we use a model to calculate the sublimation losses, we're seeing that they're 20 to even 40% on the north face and ridge top in that environment. So it's necessary to account for this redistribution in some way. As we move down into the forest zone, we have substantial interception of snow on the forest canopy. It sublimates from the forest canopy. It also drips from that canopy in the spring and plops off, sort of falls off as unloading or from that canopy during warm periods. And so we've had intensive studies of this generation at various times to work that out. This photograph here is just to remind me to mention that the groundwater storage in the basin through some very deep overtill unconsolidated aquifers. And so we do have springs of fairly warm water that keeps the snow melted in certain spots and keeps the stream flowing through the winter. Because we have forest clearings in the area, we can see how much snow is intercepted and sublimated by the adjacent forest. And you can see vast differences. These are snow survey results in a clearing near 100 to 120 millimeters water equivalent. In the nearby forest, it's 30 to 50 millimeters snow water equivalent. So we see in Marmot Creek, by comparison with other sites in Europe, in the Alps, in northern Canada and the United States, we see that we're losing 60% of the seasonal snowfall to sublimation of intercepted snow in this environment. Appears to be one of the highest in the world, is due to the warm winter winds, the fen-like winds called Chinook in the area. The Chinook wind can sublimate large amounts of snow. We can look at varying flow pathways. This is a model result actually looking at the upper part of Marmot Creek to look at the change in flow pathways during a rain-on snow event that generated the June 2013 Calgary flood. And we can see the large inputs of rainfall occurring onto an existing snowpack in June. Here's the stream flow picking up. But here's a change in flow pathways. It was dominated by subsurface runoff and a bit of groundwater flow and evaporation loss before. And then during the heavy rain on snow event, we have a shift to overland flow occurring for several days. And that very quick overland flow then helped generate the very destructive flood in this environment. My colleague Masaki Hayashi from the University of Calgary has studied the effects of these unconfined aquifers and how this important role they have in mediating the flow to the stream. And they certainly play a role in hydrological resilience in this environment, having loose materials over the heavy clays that we see in this particular environment can take a very sharp series of inputs and create highly smooth outputs. And really, we're always seeing most flow generated in Marmot Creek is ultimately groundwater flow at some point along its trajectory. So we've used the cold regions hydrological model to simulate this. As I mentioned before, it has the hill slope processes, the snow processes, the evapotranspiration, the energy balance processes, groundwater. We've included glaciers more recently. We have a frozen ground simulation, which allows us to calculate the frost table and keep the water flow perched on top of that frost table as we have thawing frozen soils throughout the year. And so we've had some success with that in this environment. This is a CRIM model structure applied to this sort of mountain basin with canopy dealing with interception of rain and snow. We calculate the long and short wave radiation, blowing snow, albedo decay for snowpacks, a snowpack energy balance, radiation for evapotranspiration. We have a permafrost module in there for frozen ground or seasonally frozen ground, infiltration to frozen and unfrozen soils, evapotranspiration, open water evaporation, hill slope flow and groundwater through here, and then routing. So and that's one particular structure. You could have very different structures here, and you can replace different process algorithms in these various boxes depending on your preference. Maybe you like Penman-Monteith, maybe you like Priestley-Taylor, not a problem. Maybe you like a bit of both in there, depending on whether it's a wetland or not. You can do all these things within the model. So then we need to work out those hydrological response units, and we can use things like digital elevation models and land cover maps to come up with these using ArcGIS intersect tools, and then come up with a series of subbasins with HRUs, and that's how we set it up for Marmot Creek. I won't spend much time there. So the key here is parameterization rather than calibration. So we have topography, drainage, and routing, because we're fortunate enough to have a LiDAR map, a LiDAR-based EM of this area. We have vegetation from aerial photos, leaf area index measurements, site visits, and now LiDAR in that environment. We have soils and groundwater from early test well development in the 1970s and 60s. We have soil pits in a regional soil survey. So we could set a lot of our parameters with great confidence in Marmot Creek, better than you could anywhere else. It's quite useful, but then we can falsify the model to show how important it is to have cold regions process representations in there. And that's what I'm going to show you. So here's a version of CRIM with snow redistribution due to wind and due to forest interception taken out. Also the effects of forest cover on melting, on controlling the snowmelt rate, and on interception of rainfall are taken out. And here's the ability of the model with parameters set from knowledge to calculate the snowpack in the alpine area on a north-facing and south-facing slope. And the points you see here are measurements. The red line is the simulated snow accumulation. The black line is cumulative snowfall. And you can see that the measured snow accumulation is far less than the modeled accumulation on the north-facing slope if we ignore redistribution. We have a very high root mean square difference between observations and model bias is quite high at 2.55. On the south-facing slope, which gets the drift, our observations are greater than precip, than the winter snowfall, and much greater than the model predictions in this case at all these sites. So that itself shows the problems there, and again, high root mean square difference. If we go down into the forest, into a spruce forest, again, we've overestimated the accumulation there by ignoring interception of snow in the winter and have a high error. We do not too badly in a clearing in the forest because there is no forest in the clearing. There is no blowing snow, and the model matches that quite well, which suggests that the belt components are still okay in a clearing. But when we try to forecast streamflow, predict streamflow from this, we do not very well. We have a very poor simulation of the hydrograph, a low Nash-Sutcliffe statistic of 0.22, bias is pretty high, root mean square difference is pretty high, and even the annual yield is off for seasonal discharge. We're simulating too much water coming out of the basin in most years, and we're missing the peak in all years. So now let's put the blowing snow, snow interception, forest canopy, subcanopy, interception of rain and snow back into the model. When we do this, we're able to simulate quite faithfully the observations of snow in the alpine environment. It's not perfect, but it's much better. Our root mean square differences are much lower. Our model biases are much smaller. When we go into the forest, same thing. We're now capturing the subcanopy snow development in the forest, and we have not degraded it in the forest clearing. And our root mean square differences have dropped quite a bit. Mean biases are much better. When we take that and then try to predict streamflow, it's better. We have a Nash-Sutcliffe of 0.58 now. Mean biases are fairly small. We're getting a little better on the annual discharge and the peaks through the whole system. So that's encouraging. And if we look at the improvement in prediction by including those processes, we'll see that by adding redistribution, the Nash-Sutcliffe increased dramatically. Root mean square difference dropped, mean bias became very small. So that's encouraging. So we say, aha, fantastic job, we've done very well. But have we? We can take a look at these results and look at the mass fluxes that we've modeled here. And by setting them up on parameters that we thought we understood quite well. And the concern is that the actual evapotranspiration is tiny in this modeling simulation. And but we have a large groundwater flow, which is developing, in fact, too much. And so also our changes in subsurface storage are tiny through the basin. So the annual values for evapotranspiration and subsurface storage change are far lower than we know is the actual case. So we have an error in our parameterization in this case for surface water and groundwater. So despite good snowpacks and good streamflow simulations, this is an absurd model and is not useful for hydrological cycle prediction. So what do we do? Well, we could calibrate, but instead we dug soil pits and started looking at various forest soils and trying to improve the rooting zone parameterization and the links to groundwater that we have in this model by instrumentation over several years and better understanding of that. And so we use that to add to the model a new component which calculated Darcy flow velocities and basically calculated saturated and unsaturated flow velocities based upon a Darcy velocity through the model. We're able to estimate soil storage by depth and porosity reported years ago by Beck in 1969 and use Brooks-Corey and other relationships to estimate the hydraulic parameters in the soil. When we did that, we were able to evaluate against measured soil moisture in various environments, and it's always difficult to compare to one soil moisture pit, but it's not too bad in many years. Taking that, we can now try to simulate streamflow again, and we're getting a much better streamflow simulation. Our snowpack simulations haven't changed, but our streamflow simulations are far better. And we're getting Nash-Sutcliffes now of about 0.71, which is adequate, and the mean bias remains small. So better physics, better simulation in this case. So now we're going to upscale from a basin we know very well, which is Marmot Creek, which is located about in here, to the whole Bow and Elbow River basins, which drain into Calgary, Alberta, because that's where the flooding is occurring. So now we're jumping from 10 square kilometers to 9,000 square kilometers and much poorer information. But we're going to transfer information from Marmot Creek to this broader area, as well as a few other research basins we have in the zone. Fortunately, we have good land cover maps of the area from the Alberta government, the agricultural zone, the forested zone, and the high mountain zone through here. There's the city of Calgary down in here. We set up 2,837 hydrological response units, and we had to include glaciers at the very highest elevations. We have glacier studies that I won't have time to talk about, but they informed the high mountain glaciarized parameterization of the model as well. And we set up the model for the Elbow River, the Lower Bow River, the Upper Bow River through here. And here's the town of Banff, Alberta. So this is the Banff National Park World Heritage Site. And then when we set it up with the hydrography, it's very complex, 167 subbasins. 41 of those subbasins have glaciers in them. We drove it. We didn't have the weather data to drive it, so we drove it with the WRF model at 4-kilometer resolution run over this area by Yang-Ping Li over 15 years. And I won't go into that in detail other than 4 kilometers seems a suitable resolution for the mountains. If we look at the ability to predict the Bow River at Banff, it's encouraging. This is without calibration, but we did bias correct the WRF precipitation in that area to Streamflow based upon the observations that we had available. But we're able to have a small bias because of that adjustment of the precip volumes. It was just a simple adjustment factor, but it's able to achieve a very high Nash subcliffe in this basin. The low flows aren't great, but the peaks in the summer flows are quite good without calibration. So that's encouraging that we can transfer parameters from research basins such as Marmot Creek and Peyto Glacier in this case to a much larger basin and still not lose much in model predictability. We also have been comparing these to other snow surveys in the area, and the results look quite good. This is in fact a technique that Russian scientists have used for many years with their network of research basins and then larger basins and parameter transfer to larger basins. So this is not a technique that we developed first, but we found applying this technique, which the Russian Academy of Sciences has used for many years, can be a very successful approach to prediction in poorly gauged basins such as the Bow. So what have we found from all this? Well, one is that, apologies for the artwork, hydromythology can be fought. We can fight myths. We can use our understanding instead of calibration and still succeed as hydrologists in producing useful prediction for society. A few conclusions, and I mentioned many research papers which you can access from this site down here below, the list of pubs at usas.ca/hydrology-old, and a few conclusions for you to think about. One is that intensely instrumented observatory catchments can help improve our understanding of hydrological processes and our ability to predict hydrology. And in fact, we need networks of these around our large river basins so that we can transfer parameters and understanding from them to the larger basins. If we do that, we can simulate certainly cold regions hydrology without calibration if we have the appropriate processes represented in the model and reliable observations to estimate parameters or to transfer them from research basins. And we showed we were able to do that jumping from Marmot Creek to the Bow River Basin. And finally, improving a model is a viable alternative to calibrating a model when applying it to challenging situations. And so when we could have perhaps calibrated the subsurface parameters, instead we decided to develop a new soils module, which included a more realistic, physically realistic subsurface flow velocity based on hydraulic conductivities and effects of unsaturation of those conductivities. And that greatly improved the model. So I'll wrap up there. I wanted to wrap up a little bit early so we have time for questions. And I know it's very late in the day in Europe and even later in Asia. So thank you so much.
Professor Pomeroy, thank you very much for this very interesting lecture. I see I look strange on the screen because there is no light and I'm illuminated only by the screen and your presentation slides actually. Very interesting. Indeed, for Russian scientists, it would be very interesting to look at all these results and perhaps to use the models you have been presenting, because the conditions in many areas in Canada and in Russia are quite similar. I also should say we had a student, Dave Kesson from Canada, who was doing his MSc, and now he works on Deltares in Delft. And he was developing the model for subarctic catchment called, let me see, I can't remember the name, but anyway, we indeed, he was struggling with the problem of trying to evaluate snow water equivalent, and he was using the different products like Globe Snow 2, SW product and such like. So it was really a challenge to do hydrological modeling for this type of catchment.
Yes, he's just joined us actually in Canmore, Alberta. So
right. Oh, say hello to him. Oh, good.
Yes, he's in the Bow River Basin now, and as a student for Professor Martin Clark, who works with me out in the cold water lab there. So, yeah,
right.
So,
that's excellent. He was one of our best students 2 or 3 years ago at IHE Delft. I'm with IHE Delft Institute for Water Education.
Okay.
Right, but we have to move to questions from this chat, and we have a number of questions here posed. Okay. I would like to first pose the question from Nikolai Yasinsky. Professor Pomeroy, as far as you mentioned CRHMP, so this model, cold region hydrological model, what is your attitude on using PC raster in hydrological modeling? Is this model available to some extent for using it in research?
Yes, the model is freely available to download, and you can see the code and all that. So that's it's on the site. In terms of other modeling approaches, we're keeping CRIM going, but we're also looking at newer approaches, which are based upon triangulated irregular networks, and in fact adaptive TINs, so adaptive triangles, which have different sizes based upon the heterogeneity of the basin. And so we called that one the Canadian hydrological model. We've just been publishing on it in the last year or so. It's not quite complete. It only has snow processes at this point, but it's able to run as small as sub 100 meters resolution when you need that, and then go up to much larger, coarser resolutions when that's needed. And so there's, and that takes, uses a full raster approach to discretize the basin based on topography, soils, vegetation, and other aspects. It's much faster than straight gridded approaches of fixed grid sizes.
Right, thank you very much. So for others, PC raster is the GIS, and in fact developed in the University of Utrecht in the Netherlands, and then HBV semi-distributed model added on top of it, written in Python. So that's yet another platform that is also quite widely used. Mm-hmm. But it's not as sophisticated as what you have presented. Now, next, yes.
HBV we evaluated many years ago when it came out for application in Western Canada, but we felt it wasn't suitable because of the non-contributing area, the issues of frozen soils, the need to move to energy balance snowmelt because of failure of temperature index approaches, and other concerns with it in this environment. So.
Right, thank you. Next question is from Dr. Vsevolod Moredo from Institute for Water Problems. Professor Pomeroy, do you account for preferential flow and loss to fractured aquifers in the model?
We do. I showed in the diagram a quick macropore line through there, but we allow for fractured flow to bypass flow from upper soil layers down to deeper groundwater, and also to, but we don't allow for that in the deeper groundwater system itself, simply from the surface to groundwater connection. So the the subsurface components of the model are far simpler than the surface components, and so we have partially addressing fractured flow, but not completely, not as completely as we should.
Thank you very much. Now, next question is from Dr. Mark Erlich from France, who is very active during this school. He's from EDF. Professor Pomeroy, given an alpine character of your study area, wouldn't it be a case for a multi-hazard, floods, avalanches, debris flows, landslides approach?
Yes, we've added avalanches to the model, and that's a component I didn't discuss, but we, based on the research of Bernhardt and Schultz in the Alps in Europe, we have not added debris flow components to it, but because of its modular basis, it would be fairly simple to add debris flow to this. Right now, we're adding soil erosion components and water quality components to it, primarily for agricultural environments, for prediction of nitrogen and phosphorus. But we have not added the debris flow components. That's a very interesting idea because it's a problem in our region.
Right, thank you very much. And I would like also to communicate the comment from Dr. Mark Erlich. Many thanks for Pygmalionism warning to the hydrological modeling community.
Okay, great.
Yes. Right, next question is from AG, whoever it is. Professor Pomeroy, do you believe that it is possible to develop a workable model without any calibration for more or less large river basins, without using research basin as a proxy basin?
Yeah, it's, I think we're not there yet to totally avoid calibration in that case. Many of the routing parameters in particular would be improved through calibration. On the same river basin, I've showed the CRIM results, the Bull River Basin. We also ran the mesh hydrological land surface scheme model at 4-kilometer resolution. It's a gridded model. It has different land covers, and we've added slope and aspect, elevation, and glaciers to it. We're able to get a very high Nash-Sutcliffe 0.79 from this, but through calibration of routing and some of the subsurface flows on it. So further improvement required that. In this case, but when we apply that model in areas where we don't have research basin results, we have to rely much more heavily on calibration in order to obtain reasonable results. So it's so the research basins are crucial in doing this. It's something we've started to address in Canada. We have now 60 research sites, observatories we call them, as part of the Global Water Futures program across the country, which is reviving really the old idea of the International Hydrological Decade. And we will be using these in our Pan-Canadian modeling program.
Thank you very much. Next question is from Dmitry Pershin from Russia. Professor Pomeroy, how do you see the future of ground-based observations and simulations of snow canopy interception?
There's lots of interesting developments in this right now. It's always very hard to measure how much snow is in a forest canopy. And people have used gamma radiation attenuation. I've cut and hung trees from electronic load cells from a tower to capture that, but you can do one tree that way, not many. But what we're able to do now is use LiDAR based from drones flying at low elevation over the canopy and measure in great detail the snow, excuse me, the snow in the canopy, as well as the snow under the ground on the forest floor, with millions and millions of LiDAR returns. And that is proving very, very useful. Also, it looks like some scattering of GPS signals holds promise for estimating snow mass in the canopy as well. So those are two that I see observationally moving forward. It could be very, very good. And then, of course, with smart sensors, now we can have many more sensors on the ground and get that spatial variability that was always so hard to capture even 10, 20 years ago.
All right, thank you very much. Another question from Dr. Moredo. what would you recommend for establishing an observatory catchment with a good upscaling capacity?
The catchment needs to have land cover types within it that match the larger region. It's transfer of these land cover parameters rather than, it doesn't have to have the same shape or other aspects, but it needs to have the same land cover types to move forward. That's been crucial for us. It's helpful if it has similar geology and to that as well. But I say otherwise, it's geology and land cover, and then be in a precip zone that is at least close to the what you would have over the basin you would extrapolate it to. Otherwise, you could have very different phenomena occurring that make it hard to pull these parameters out and use them in large-scale models.
Right. Thank you very much. Next question is from Dr. Pelagia Bellikova also of the Institute for Water Problems in Moscow. How honest it is to transfer parameters from a well-studied catchment to a larger catchment where there may be another ratio of soil types, the hydrophysical properties, and so on? Is it a lumped model or distributed, which could account for these differences?
With the distributed model, we had of course used transfer functions to relate the soil properties in the larger area to what we're able to confirm in Marmot Creek and elsewhere. We used more than Marmot Creek for that. We had pretty good soil maps for the agricultural region, and in the mountain region we had poor soil maps, but the mountain soils tend to be very, very thin and less important. So we knew the elevational change in soils from Marmot Creek. We could take that to the mountain region, assume that still held. So I think that was reasonably rigorous, and apart from some winter base flow problems, which you could see in the model simulations, where we clearly didn't have it exactly right for groundwater, but at least for the summer flows, it was quite a good approximation.
Right. Thank you very much. Professor Pomeroy, I would like also to say that indeed the modeling for cold regions could be quite different from modeling for tropical regions and for moderate climate regions. So every type of region has its own specific features which are to be taken into account in the model structures and models parameterization and components of the model. So many people who are attending this school actually are coming from regions where climate is quite different and different types of catchments. But I suppose, as you said, they could still use your modeling structures that are downloadable from your site. Maybe you would be interested also to communicate with them further, even if ladies in their or people in their countries are not so frozen as the lady on one of your slides. Part of it is completely white, so obviously that model that the lady represents was developed for cold regions. And I would like also to send the statement from the YouTube channel that Adolfo Lopez Perez says, don't calibrate, improve the model. But with this, I would also like to say that in many cases, people don't have so much data as you had in your experiments, of course. So parameterization is great when you can measure all these parameters of the model. But if you can't, then still you need to develop procedures that would lead to reasonably accurate model, if not terribly accurate. But of course, to calibrate the wrong data is wrong. So so the truth is perhaps somewhere in the middle here. So you have to be clever in how you approach the modeling exercise. Professor Pomeroy, so we would like to thank you again for being with us during these difficult times. Also, you had to wake up very early, we know. We tried to move your lecture to a later hour, so that you wouldn't be waking up at 6 o'clock in the morning, but maybe at 8 or something like this. Thank you again very much for attending, and would like to thank you again, the whole audience, I'm sure, applauding you. Really exciting, igniting lecture. and it would also, especially your first slides, interestingly raise the questions which are to be answered by the hydrological community in the coming years and decades. Professor Gelfand, maybe you have some final words? Unmute, please, your microphone.
Yes, I know works of Professor Pomeroy very well, and I highly appreciate his works, and I'm very happy to have another opportunity to study his work now. So thank you very much, Professor. Thank you very much. Your lecture was very useful for our students, and was very useful for not only for the students from Water Problems Institute, but for students from all around Russia. Thank you.
Again, thank you very much. Yes, audience. Sorry, Professor Pomeroy, I interrupted you.
No, just saying thank you so much for having me. And I wish we were in a world where I could be sitting in Moscow with you and enjoying the dialogue with the students, but that world will come back. Thank you.
We would love to have you in Moscow during this wonderful weather, by the way. Today, 23 degrees outside. So it would be really great to have you during this school. So we hope still to organize school face-to-face some time later. So I'm sure these contacts will continue. And I would like to remind the audience that tomorrow we convene, so Thursday, the 4th day of the school, we convene at 3 o'clock in the afternoon, Moscow time. So it's 2 o'clock p.m., 2 p.m. Central European summertime. And we start with Professor Yi Zheng's lecture, and then followed by lecture of Florian Pappenberger, and then Jeffrey McDonnell. So everybody, thank you very much. Connect tomorrow. We'll see you later.
Thank you. Bye-bye.
Thank you.